Hello and welcome to this introductory video on the photoelectric effect. In this video, we're going to take a look at this photoelectric effect experiment. We're going to set it up, think about what might happen using our classical physics background that we've gained so far, and then we're going to actually discuss what really happens. And in a later video, we will make sense of the discrepancies between our predictions and our results. So what is the photoelectric effect? It is the observation that if I take some piece of metal here and I basically shine light on it, so I've got a light bulb, that's a light bulb, there you go. So I shine some light on my metal and I connect by some wires and an ammeter, say, over to some other plate here. I'm shining light onto that one. Then, on occasion, what I will notice is that I do register some current flowing through here. So the idea is that basically this light can stimulate the electrons in this metal so much so that the electrons can actually be ejected from the metal and they can move and maybe eventually hit this other plate, completing the circuit. Okay, not all of them necessarily go there, but if we're reading some current, then that's what's happened. That's the basic idea of the photoelectric effect. And of course, the actual design is a little bit more complicated. Typically, you also have some electric field here to guide the electrons over there. And then sometimes you actually reverse that field to determine things like what is the maximum energy of those electrons as they leave the plate. So if I put a field which is actually trying to repel those electrons, then based on the strength of that field and hence the potential difference between these plates, I can infer what the energies of the electrons are given the minimal value of the field required to stop any current flowing and things like that. But those are extra levels. This is the basic idea of what we're looking at, just that this electron, by having the light shine on the metal, the electron has gained enough energy to escape the metal, and then it encounters the other plate, completing the circuit, flowing back around, and returning to where it came from. So let's think about this kind of thing in the context of our classical knowledge. If we imagine plotting, say, the current as a function of time, then I'll use A for the current here because I want to use I for intensity of light later. So this A is like our amps, reminding us that we're talking about current, let's say. So classically, what we're saying is maybe the first bit of light doesn't quite give me enough energy. So I'm not going to get any current out initially, but after some time, this light is going to build stuff up. So at t equals 0, I turned on the light. It's now dumping energy in there, and finally at some point, the electrons have enough energy that I get maybe some small current out. And this time, let's call that sort of T1, the time when I first start measuring current. Now, that depends on how long it took, basically, to give enough energy to the electrons in order for them to start giving us this current, have enough energy to escape from the plate and complete the circuit. So that just basically depends on how quickly I'm dumping the energy in. Now, we've introduced that the photons have an energy, which is E equals hf. And so you can see if I start changing, say, the color of this thing, so I make it bluer so that the frequency goes up, then I'm dumping energy in faster, which means that I expect that T1 should go down. And vice versa, if I make the light redder, then the frequency has gone down, and therefore I expect that T1 should increase because it will take longer to reach the energy required if I'm adding energy sort of slower because I'm adding lower amounts of energy. On the other hand, I could, instead of changing the color of that, I could just add a second light bulb. And if I've added a second light bulb, what I've done is change the intensity of the light. So we'll use I for the intensity here. That's why I've used A for my current over there. So the intensity of the light is just how much of this light am I actually shining. So I've changed the number of light bulbs, not the frequency. So I doubled the light, say, by adding that second light bulb. So I've increased the intensity. If I've got twice as much light hitting the thing, well, then it stands to reason again that I'm dumping energy in faster, and so T1 should again go down. So not only does the intensity decrease T1, but you would also expect that if the intensity is higher, you probably get a larger current, because once you reach that level, you would go and be dumping energy in fast enough to free more electrons at the same time. So you would expect that the current goes up. And actually the same thing with frequency, you would probably expect that your current goes up as well. So these are my expectations for this system interpreted in this classical sense. Those are the expectations. So what actually happens? Is it always good to ask? Let's test our predictions and do the experiment. And this is where things get strange and really weird, in fact. The first is, if you plot the current as a function of time, well, you get two choices. Either nothing ever happens, or you basically instantly get current. So either you get the current, or it's forever zero. Very strange. Then you decide, well, okay, we got the timing wrong. Fine. Let's see what we can do about that. Let's explore the dependency on frequency. So let's now plot current as a function of frequency. What you find then, in reality, is that you will get no current, no current, no current. At some certain frequency, it switches on. At more frequency, it just continues. Strange. So the last thing to consider is what happens with the intensity of this thing. If the frequency is high enough, then we will get a current. And if I increase the intensity now, then that does increase the current. On the other hand, if the frequency was not high enough, so I was generating no current, increasing the intensity has no effect whatsoever. All right, so it's again kind of like this one where it depends. You either have current or you don't, but at least when you do have current, increasing the intensity does increase the current. So that's about the only prediction that we sort of got right. Why is that? We'll see in the next video.